Is the screen visible?
Yes, sir.
Yes, sir.
Okay, good. So, in today's class, mostly, you will see the magic of learning. Mostly, I think you will all appreciate. Many of you know, and many of you will appreciate, and it looks like a magic what I will show you today after some time. I mean, the proliferation of learning and what it can do, what it has achieved right now, and what is its potential. So, when we talk about convolutional neural network in broad sense, so I just have a brief name like CNN. So you can see that we are looking at spatial relationship, right? Because in an image, when we talk about convolutional neural network, in an image, we are trying to locate the spatial dependencies and try to equate with some other image, as I have shown in the last class, maybe an x in this way, an x written in this way, both are equal. By looking at the spatial dependencies of that, and therefore the rotations, revolutions, and all these factors we can cater to. However, in many a times, we need to model not only the spatial dependencies, but also something called as a temporal dependency. So in colloquial machine learning terms, which we call as a sequence modeling. So it means that suppose I give you a pendulum position and give you a snapshot of it. Now, can you tell me whether the pendulum is going this way or this way? Suppose the full swing is this much, from this to this is the full swing. We cannot tell, right? Because if we do not know its previous positions, we cannot tell. But suppose I give you at the previous time it was here, the previous time it was here, then you can obviously tell it is moving in this direction, which means that there are history that sometimes helps us to predict something in a temporal sense. So this is part of sequence modeling, and which we often deal with something called as a recurrent neural networks. So sometimes we call it as an RNN in short to deal with such kind of predictions in terms of a deep neural networks. So we will see today first the frontiers of what we can achieve through these recurrent neural networks. So if you look the traditional classification problem where we have an artificial neural network to classify. So you can see you get an X and you predict a Y. Suppose you get that whether you get the attribute and the previous CGPAs of the student, and I need to predict the ML grade of this student. Whether it's a, I mean, if it is a binary classification, I will just predict it he's a pass or fail in ML grade. So this is one of the binary classifications, and you can see that the interim network can internally take different layers of operations and then finally produce the output. So this is what we typically do. However, in many operations, sometimes we need to see that the temporal dependency that we are talking about, because many a time, suppose look at this sentence that machine learning CS 60050 course will be very helpful and applicable for any student to practice and apply ML to solve real life problems. And I want to hear about the sentiment after looking at this. Suppose this is a Twitter post. What is the reaction to it? So therefore, you can see its modeling is not dependent on a particular instance to look into and give a grade, give a outcome, but also it depends upon the sentiment or depends upon the juxtapositions of the words we get in. So here you can see if I say the position of the word is x1, then I look at the word x2, then I look at the word x3. So my neural network needs to carry forward certain information to its the next counterpart and its next counterpart to finally give me an output which is a sentiment. Let's say it's a smile, it's a hopeful statement or not. Similarly, look at this caption. So this is we call as many to one kind of a classification where we need to look for many possible temporally dependent inputs and then need to predict certain output with the dependencies and through the neural network in it. Look at this. Many of you have now seen that if we have an image, there is an automatic caption going on over the image. We can automatically give a caption to the image. So image is just a one input meaning that we have a metric that metric captures the image information, that is our X, it's a metric. And we pass it, and looking at the different positioning of the image, whether he's running, whether his ball is in hand, then we can say what kind of dress he is wearing. We can say it's a basketball game. Then he is throwing the ball depending upon his arm. So therefore, here you can see the basketball as a game, throwing the ball. Then this is basketball player throwing the ball. This whole statement gradually we can make out passing through the neural network a sequence of things. So it is not only that basketball as a game has a last say, because basketball as a game has the option of throwing. So it need to propagate certain information to the next layer, so that, because if it is a football, there is no option of throwing apart from a goalkeeper. So if a general football player, there is no option of throwing. So some of the history or temporal dependency comes into picture. Look at the third example. So there are other examples of such kind of a thing. Suppose we are predicting the weathers. So you get a certain representations of the particular location, and you predict the rainfall, you predict the wind, you predict this thing. So there could be many such examples. Look at this machine to machine translation. I hope you have noticed nowadays that Google, if you write something in your English language and can choose any native language, it translates it, right? I mean, whatever you write, it can directly translate. I mean, translating means that it's an English to that language translation, not you are writing English, your native language, in texting in English. That is not the case. But you are writing an English statement, it is just transferring the meaning to the same language. Now here you can see that we take the statement as a whole, which is a multiple input words, and then it can also produce multiple output words. But it needs to progress through the temporal dependencies of the previous layer in order to accurately deduce the semantical meaning of the sentence and can produce an output. So these are some of the applications where recurrent neural network has grown its importance. And two things to notice here is that it's the recurrent thing that dictates the temporal dependency, and due to the sequence modeling thing, you can see the network is deep, because you can see the width, and obviously the breadth is also deeper because of the neural network predicting something. It needs to be propagated to this deeper thing. So the simple extension that we make, if we want to dig down the theory a little bit, now the simple extension that we make over our general artificial neural network here. So this is our ANN, which takes an input X, predicts output Y hat. So the general extension we make here is that this, we would say that the input at time t and the output at time t. And also, after saying this, we will say what this value, this network information can I propagate to the next point, so that at time t plus 1, taking the input at time t plus 1, I can produce the output at time t plus 1. You may also resemble this one with the hidden Markov model kind of a concept, just unfolding the network with respect to time so that we capture the temporal relationship. So similarly, the recurrent neural network, the generic structure, if we elaborate, it would be so I put here xt, I put here xt plus 1, I put here xt plus 2. For one to many, this xt plus 1, xt plus 2 would be the same. For example, the basketball game, I will give the same image every layer. However, the output will be different as the statement builds up. yt plus 1, yt plus 2. So internally, in a broader sense, if you look at this is basically your recurrent neural network is basically a block which is taking an input at time t and producing an output at time t. However, it also has a loop into it which can take the previous hidden value of the internal nodes and can fade it to the next node. So this means this is the hidden value at time t faded here. This is the hidden value of time t plus 1 faded here, and we move on. Right? So this is the basic recurrent network structure. And therefore, mathematically, you can understand that yt hat is obviously is a function of xt, and whatever information that I propagate from the previous layer. Right? So this is a fundamental recurrent neural network. And why it is used, suppose let's say it sometimes is used to predict the next word. Suppose I can say the clouds are in dash. Now it is very easy to understand that this is obviously this is a very simple statement. However, the complicacy arises, suppose that I grow up in Bengal, then I say many statements that I studied here, I did my faculty position here, and then finally I say I speak fluent dash. Now obviously you can see here the recurrent thing is a very tricky issue because this sky is very near related to this. This sky has a temporal dependency very nearer. However, here the thing that will come has a temporal dependency very far, right? I hope you can understand by these two examples that this problem is tricky because how much we will unfold and how much informations I need to propagate to understand what will be here is basically not very easy. Right? Yes or no?
Yes, sir.
So therefore, the same algorithm of backpropagation and neural network learning we will use, but it will be backpropagation with respect to time that we will incorporate. So what will happen is this, that here you get xt, or let's say x1, here you output y1, here you get x2, here you output y2, x3, you output y3, x4, you output y4, and so on. Now, you can see that in traditional neural network, there is only one part, so there are weights inside it. But here I need to propagate certain values. So therefore, there will be weights from hidden layer to hidden layers. There will be weight from hidden layer to hidden layer. So this is a metric. There will be weights here in the dimension of x to hidden layer. There will be weights from x to hidden layer. There will be weights from hidden layer to y. This node. Weights from hidden layer to y. So all of them I need to learn now in order to update this network while training, right? Because in neural networks, flatly we learn the weights during training and backpropagation. Now you need to know the weights. And obviously in mathematical equations, if we need to update the hidden states, what we do, if we need to update a state at time t, usually we follow this kind of a smooth function, tan hyperbolic function, which will be the hidden layer with respect to t minus 1 value of the previous layer, and xh with respect to the tth value. So as you can understand that tth value goes in here and the previous layer hidden out input comes in with the weight. So this is the previous layer part and this is the present input part, and that's the update that you make in the next propagation. And when you go for the output updation, so you can see that output updation, this is predicted output updation, is nothing but transpose into hidden layer of T. Okay, so we will output the update based on the current position of this hidden layer. Depending on that, we will output the update. So combining these two, earlier in neural networks, as you can see in our neural network setup, so the general ANN setup, what we do is that we update Y based on W dot X, right? And obviously we pass it over the theta of the sum over this, we pass it to the nonlinearity and then update it. Now what we are doing is that we are calculating this H. Yt is dependent on H. Effectively, this is our X right now because my X is now a complicated function which is from the previous layer and the current input side. I hope this makes a sense with these two analogies that we have. right? This is how we update the weights, update the hidden states and update the output variables.
Sir,
Question? Yes.
yes, sir. Sir, I have a question. That is, here we are using activation function as a tan wage, and we have
Yeah.
other activation functions like sigmoid function or ReLU function. My
Yeah, you can
question
use
is,
sigmoid. Yeah, you
uh,
can
my
also use
question,
sigmoid.
yeah, my question is when to use which function?
Oh yeah, I will tell you just after this. I mean, we have a ReLU function, we have a theta function. I will tell you. Just wait.
Okay,
After this slide, I will tell you.
okay,
So there is a problem that will happen that I'll discuss and I'll tell you that. So now the thing is that what you need to do as you do the loss calculations and go for back propagation. This is the front propagation, as you can see that HTI compute from the previous layer, YTI computed each layer. Now obviously there will be a loss that you need to compute. And during back propagation, that loss should be propagated through this every layer. This is how we do in back propagation, remember? Right? Similarly, I mean, this weight also will be updated. However, here a new thing that comes up is that not only you only back propagate through individual neural network layers, but you need to also back propagate with respect to time as well, because your update value in this hidden state is also dependent from the previous state as well. So there comes the only change in the back propagation algorithm. We call it as a back propagation over time, because we back propagate the whole thing not only through individual neural network but also over the times. Okay, and the same kind of mathematical equation will be there where we will try to optimize the gradient, and by taking the del over all that, instead of taking only the del over only one particular set of layers, you need to see how the impact is coming through this way as well as this way, how it is coming in both sides. So this is what we make the change. Now, one interesting point which will eventually come to your friend's question is that, see, this network could be very deep, as I have shown through this example, that sometimes the context is far away from its temporal dependency, and we need to store such kind of a deeper network. As you can see that if the temporal dependency that I grow up in Bengal has to do something with I speak fluent which language, it has a dependency much later than the occurrence of the context. So therefore, I need to grow this network very deep. Now, two things may happen. See, when you propagate this, make a gradient descent, propagate the gradient, what will happen? I hope you remember, it is output into 1 minus output as the derivative of this thing, right? You remember, right? The derivative of this thing is derivative of theta dot s. If you take the theta dot s is 1 plus 1 by e to the power minus s. If you take a derivative of that, then this will be nothing but theta s into 1 minus theta s. I hope you remember. Yes or no?
yes, sir, yes, sir.
So you can see that this value keeps on multiplying itself while going on, and it will be multiplied with y, and then again this and this and that. Now the problem is that if this value is greater than or very high, then we have explosion in the gradient, because the deep the layers are, you keep on multiplying this with the next, with the next, with the next. Your gradient values keeps on increasing and exploding. For that, you need to normalize and reduce the gradient value, and this is the easier thing. I mean, the easier problem. We can tackle it very easily. But the other problem is very difficult to tackle, because Bengali has an association with Bengal far behind, and if my gradient value is very small, it's a 0.01, then till I reach to this position of Bengal to catch from this network, my diminishing gradient almost reaches 0. So I could not propagate any information from this layer to where I want this Bengali to happen. Right? So this is typically the problem which we face, which is called diminishing gradient. In backpropagation, this diminishing gradient is a very vital problem. Now, how to cope up this diminishing gradient problem? 2-3 things we need to think of. That your friend has already given a clue that we need to think about the activation function. How the derivatives of the activation function looks like, how it diminishes. And it has been seen that the derivative of ReLU looks like something this. The derivative of hyperbolic tan looks like something this. The derivative of sigmoid looks like something this. Okay, so this one is ReLU derivative. This one is sigmoid derivative, and this one is tan hyperbolic derivative. Now, depending on that, which of the derivatives will give me what kind of value to so that it could be preserved, I will choose my activation function. Get your answer? Yes or no?
Yes, sir.
So one of the thing is that we will choose the activation function in a very meticulous way so that the derivative will not give us this diminishing gradient at long run. As you can see, if you choose ReLU, your gradient will not diminish if you keep on multiplying because it's a constant term, it's there. But if you keep on multiplying with this tan hyperbolic h after a certain point, even sigmoid is worse. So therefore, this thing uses tan hyperbolic h rather than sigmoid to be in the first sense. The second thing that we could do is initialization is a very important factor in machine learning. Initialization of the parameters, because the back propagation, when you do a back propagation and then forward moving and then try to learn something, you adjust your weights from the initialized points, you come to a minimum, right? That's what we do. And depending on the initialization, the number of iterations also vary. So this diminishing gradient problem can be nullified if we initialize our weight so that sometimes we have this identity matrix as part of our initialization. Then whether you multiply with what, that value will keep standing because A multiplied with identity matrix will keep on A, right? So initially when the weights are initialized, rather than initializing it to a random weights, people try to initialize using this. It has many ramifications, pros and cons. We do not have much time to mathematically solve all these things, but I am just giving you some pointers so that you could look forward if in need, if you have to apply such kind of things. The third thing, yes.
Sir, will you discuss the first point, that is the activation function?
Yeah, activation function means what is the diminishing gradient point? I hope you understand, because I want to predict a word long ahead than from its context. So therefore, the context where it occurs, the hidden state values from that value should be propagated towards where I want the outcome. So now, if in the back propagation, every time I multiply certain values, which is a fractional quantity, and keep on multiplying till I reach here, then the effect of this node will not be propagated here. So I need to keep it intact. Therefore, so why this derivation is dependent? Because the derivation keeps a multiplying factor with it. Now, depending on the activation function you choose, your multiplying factor will differ. So you need to carefully choose your activation function so it can give you maximum gain while your context is much before than your outcome that you need.
So, but
That's
ReLU
what
is giving ReLU function is giving the best output over here. So why aren't we using that instead of?
no, people use ReLU. Sometimes it's a overkill, because sometimes the context are like this. I am taking one example. It is not only used to predict the letter, right? It is also used to captioning. It is also used to many other things, right? Sentiment analysis, for example. So it depends on what you are using. It has a price to pay. That's what I am saying, that I am not explaining everything. All these function has a price to pay in terms of computations as well, right? And the main important point of ReLU is, since the ReLU function is like this, you can see there is a discontinuity of the ReLU function. It is 0 or max.
Yes, sir.
Right? So if you have to take a double derivative, then ReLU is not good because it's discontinuous at this point. After single derivative, it makes it discontinuous. So each has a pros and cons with the applications that you want to do. And typically people have seen that tan hyperbolic function works better. So it's a it's a totally practical or numerical no theory established on that. People go on selecting their activation function depending on the problem they are doing it. Okay.
Okay.
The third thing, which is the most efficient, I mean, apart from all this, what people do is called a gated cell. So the gated cell is nothing but, many of you have heard this thing, right? Long short-term memory. So which has basically what I do is that instead the whole sequence, I will keep certain aspect of the sequence when I need, and I will forget certain aspect of the sequence when I don't need. For example, let us again go back to the same example. I grew up in Bengal. In between whatever I say, I don't need here for this prediction. So something I will remember, something I will forget, and based on that I will update it. So therefore, these kind of cells usually have 4 parts in it. One is forget part, one is store part, that is what to remember, one is update part. So based on these 3 things, these long short-term memory are very interesting cell that people use to reduce this diminishing gradient problem. And even this is the de facto nowadays for using RNN networks. To give you a view of what is this particular thing, it looks like this, where these nodes are we call as the forget node, where it has a forget function to diminish the relation, the input side to carry forward. There are some nodes which will store and add up the values and keep on propagating, and there is certain updation function with respect to the activation, and there is an output, output propagation and hidden propagation. So this is how the LSTM thing looks like, and it is very popular in developing such kind of a recurrent neural network framework where your node will look like this. Now, each neural network, when you update using a activation function after the summation, that activation function will look like an LSTM mode. So people use such kind of thing in prediction, and believe me, what it has done successfully is one of the successful applications. Many times you will see that AI is painting new things, AI is generating new music. All of this happens due to such kind of a recurrence neural network platform. So all these things automatically can do. If I train different types of painter, it can generate a painting from this. Though painting is not fully dictated on this, we will also look into a concept just now after this, which has something to do with it. But generating music is extensively we can do it. What you need here, you can also just write a recurrent neural network and do it. You give a first tone. A first tone, you just give it and leave it for the rest. What it will do, depending on this, it will predict the next tone. Depending on all of them, it will predict this tone, and it will go on doing this. And it's a beautiful application of recurrent neural network people usually do in their lab classes in deep learning. So this is one aspect, that going deep to model not only the spatial dependencies, but also the temporal dependencies in order for prediction, in order for caption generation, music generation, sentiment analysis, and all sorts of stuff. Let us move forward, and which is the most interesting research that has been done in recent past about this deep neural networks, and the proliferation of deep neural networks starts from this thing very much. So any questions in this recurrent neural networks, the basic concepts? We are not going into the details because it need a detailed course for that.
Sir, can you please explain the how to generate the generation next stage of music and tone by
Next
using
stage of
only the
music
first
and tone, you just design a recurrent neural network. You train it, this recurrent neural network, with your first tone. Okay, you first tone, you give them train it. Okay, sorry, I'm sorry, not the training in the first one. You train it with respect to different musics. You train it with respect to different music. Let's say A.R. Rahman's music, you train it, right? Now you give
the
a
musical
random
notations are stored.
No,
The
just
series
the
of
audio.
musical notation of
No, I am saying just the audio. You train it using the audio.
training using the audio. Achha,
Just
okay.
train it using the audio. Now you give, let's say, a 2-second audio. Okay, it will generate third second first. Then you give 2 plus 1, it will generate the fourth second. 2 plus 2, it will generate the fifth second, and so on. So what you do after training a lot of A.R. Rahman's music in this recurrent neural network, it knows, it will learn a pattern. So depending on your first tone, let's say of 2 seconds, it keeps on generating the third, the fourth, the fifth, and a music will be generated. The longer is your initial tone, the better is the symmetry in the music that you will find out. And obviously it depends upon what is the input set you are trained with. I mean, obviously A.R. Rahman's music, if you are trained with, you cannot generate Mika Singh, right? I mean,
Yes.
so it also has a bias with respect to the training as well. But it's a nice exercise that it only uses recurrent neural networks, the history, to update it. And if you have this long short term memory cell inside it, you will see the difference what you make. This is a fun exercise. You usually give it deep learning courses.
So can there be another application, like if I give the first sentence, it will predict a story? So could it be done using RNN?
It does, but as I said, that story is, then you have to give a whole lot of examples for it. I mean, the whole Shakespeare, if you give it, then it will learn and try to predict the story. But the difference, I mean, predicting a whole story and a music comes. See, the abruption of the music may sound bad to your ear, but it's a music, right?
Yes.
But abruption in the storyline, I mean, if I say that I went to sea and then collect 2 flowers and come back, it looks weird.
Yes.
Right? I went to a beach and collect 2 flowers and come back. It looks weird, but it can generate such kind of a thing. Okay, so people are doing all this, and people are doing, trying lot of things, and even just after this, I mean, what I will show you is something magical. Any other questions? Okay, since we are talking about this generation of new things, which is obviously one of the primary goals of machine learning, that not only we could reproduce, predict, do something by our experience, but we could create something new. So with that, there is a concept called generative models comes up. So with this, all this generation thing, there is a concept which is called generative models. So why these generative models are known, I will just come into a little bit afterwards. But first, let me show you 3 images. Just look at top 3 images. Can you predict which one is fake? Among these 3 images.
Fake means background fake.
No, the image. I mean, this person doesn't exist in the world.
Oh.
All are fake.
Any other?
Anything.
See.
Yeah. Actually, all are fake. I mean, there is no such person. Any of them doesn't exist in the world. But I mean, since we are doing it in a class, I mean, if we give you any random people, he or she might not say that all are fake, right? So see, this has been generated by a neural network. These images has been generated by a neural network, which is obviously what we are going to study, this generative modeling through a neural network. Why does it help? First of all, look at that suppose you are driving an autonomous car and you are trying to learn the driving pattern and you are building an autonomous car. Now, most of the things, so obviously you can see your scenarios will follow a Gaussian pattern where this, use another color. So this is the normal patterns that you can figure out maybe within this side, your road, turns, some bendings and all. However, this part is the outlier part that you might get it like this scenarios. Like when you are driving, suddenly a plane is coming down. I mean, it's such an edge case that it doesn't occur in your training example. It's a 99.99% chance that there will be not such a training example, right? You have driven in rainy weather and many other weather. There would not be a training example where the sensor is foggy. Your sensor got washed with a fog kind of a thing. You have done with a very much pedestrian and all such examples. There will be pedestrian dancing inside the street, will not be yours, right? So these generative models are used to train your application that you are trying to do with machine learning to make it more robust. Because the data that set that is given to you is obviously will follow a certain good distribution. It will not follow the outlier distribution. Now, if I could build such kind of an image to train, that will help me a lot, right? So that is the whole purpose where this generative modeling starts with this neural network factors. So simple that you detect faces to open a password. Now, there could be homogeneous face colors, you get it. There could be diverse face colors, but you could not explore the enormous possibilities of this diversity, right? There could be shades, there could be brightness, there could be blue shaped things and all. So what if that I train with the given set and also by some generation of new data sets, just like these images, A, B, C. I just generate it and train, right? Isn't it be good that your model will be more robust if you could train it using those images, right? So the whole concept of this generative modeling comes from the fact that I have to generate. So given an input X, I need to generate new inputs. So let me also call it X prime. So that this is, let's say, an image is given. This is a new generated image which looks similar like from this distribution. So I generate something from the distribution which is not there inside it, but somebody will look this X dash will never say that this is fake. It looks like the same thing. It may be an anomalous case, it may be a regular case as well. So what people try to do is that they try to pass through a several neural network or feature maps, and then they provide an internal latent representation. Sometimes we call it as a latent representation. So this latent representation obviously have lesser dimension than this. So suppose this dimension is D, this has a D dimension less than this. So, but this D dimension are the critical dimensions that must be needed or required to express this image. In other words, you could also say this is kind of a compression we can do over the input dimensions, and sometimes we call it as an encoder. This is an encoder part. Now, following the same thing, we have another set of neural network nodes. So this is one direction. We just encode and keep the relevant details. And following the same thing, we produce certain new generated image from this part. Which set this is, we call the decoding part. So this is whatever I am discussing is popularly known as autoencoders. Now the question is that, see, we lose information by compression because we only keep the relevant details, the rest of the things get lost. Then how could we get a new generated image? What we do, let statistics, stochastic thing comes in. We provide a mean with this and provide a variance with this. And then we perturb this thing a little bit. You perturb this a little, you perturb this a little. So what will happen eventually when you perturb the mean and the variance, you perturb this mean and the variance a little bit, something that will get generated which will not be present in your image, isn't it? Yes or no?
Yes.
Yes, sir.
So what does it mean? Suppose in the image you have this kind of two. Now this has a little bit reduced it and maybe this something like this in the intermediate image. Now you go on perturbing it a little bit, putting in variations. So one could be you can have a little bit like this, you can have like this, you can have like this, right? So all of these are not part of here now. These are new generated image I make of two. So this thing that I just did here is called variational encoder. Variational autoencoders, or in short we call VAE. This we call AE autoencoders. So this is one way in which we generate new models. And the training and all that you can easily understand. You have to minimize the loss function from the input side to the output side. So this is the whole hierarchy where you need to minimize the loss. And your loss function, obviously, with respect to x and x dash, you can take a squared error of mean squared error, whatever you wish, and try to minimize the loss function, back propagate, and do all these things. In variational encoders, this is a probabilistic, since it's a probabilistic distribution of Gaussian of mu and sigma square. So therefore, you can just perturb this Gaussian distribution a little bit and then get a new Gaussian distribution with a new mu and sigma, a little perturb of mu and sigma, and get a new images. And then you train it accordingly, as we have seen for a general neural network using backpropagation, with all sets of images, and perturb and get a new image, perturb and get a new image. This is what we do in what we call as an autoencoder process of generating new images.
Sir,
The other, yeah, questions?
So that means autoencoder are not generative. VAE are generative.
No, autoencoders are only representing the salient features.
Okay.
Because see, to generate something to be fake, this face was of someone. Maybe the eyebrows are not like this. Maybe the eyes is not like this. Maybe the nose is not like this. I just perturb a little. But I will show you. I will show you what it outputs. I will show you. Let me tell the second method. The second method, what we follow, is the name of the method is just let me recollect. Yeah, it's called a discriminative modeling. So this is a very, this is one of the best papers that has been arrived here. It's a what people will do, how the fake things are generated. The concept is very simple. So we have a noise to start with for the X. And with that noise, we go on with the neural network to train it and generate just a fake image from this. Now we have a real image also. And then there is a discriminative model, which is nothing but a game between this real and fake, and try to update the fake image in such a way that you get a new image which looks like a real one. How does it happen? Let me give you the intuition between this. So this is a neural network. This is also a neural network. The intuition is that suppose this is the real, or rather I would say not the real. Let's say these are the real points. And I generate 3 fake points, initially a random noise of it. Now, when this 3 fake point I placed over here, it looks like this. And I keep on training over these 6 examples. Then obviously after one epoch of training, I will tell that this has higher probability to be general, this has this much probability to be general, this has this much. This has this much, this has this much, and this has this much. I train again. Then obviously after a lot of training, this probability of to be correct will reduce, and this probability of to be real will keep on increasing after much and much training. Then depending on this game, what I do at the next iteration, I try to generate examples much closer here within the realm of the new point. Still, this is not the examples that are here. And again, do the same exercise of this probability computation, which is real and fake. And after a certain time, when I could not distinguish between these, I stopped. So this is particularly, this neural network is act as a game between from the noise what you generate a fake image and the real image, and try to perturb in such a way the fake image that it looks like real through the adversarial network that you keep. Right? So this is we call as generative adversarial networks, or in short, you have seen GANs. After GANs has been introduced, this field has totally taken off. There are companies like Deepfake, which is totally banned nowadays because it tries to propagate pornographic images of the actresses. It was banned then. So it just keeps on generating such images that you could not look like. Suddenly a news came that Barack Obama is giving a speech, which is not Barack Obama, and all that. So this is how we keep on iterating over the like a game with the real data and the fake data and try to push fake data towards the real data frontier. This is what the generative adversarial models or generative adversarial networks can do. So let me now, as I promised you, let me now give you 1-2 examples that how these perturbations and these generations can help us. So see that a little perturbation on the head pose. You can see the head is tilted towards right in this. Head is tilted towards left in this. This side he is smiling. He is not smiling. A little perturbation, maybe from the variational encoder perspective, or maybe from the generative modeling that this phase doesn't exist in the pattern as well. This phase doesn't at all exist in the image set. I just created it. And more importantly, you can see that the left side, these 6 images that you can see are the real image. All of these images are all fake. Now, can you tell me that these are fake? Never, right? But if you look closely, look at this boy. It resembles somewhere here with this boy. Maybe the eyes like this, maybe the chin like this. I mean, it has just done something over this all generative adversarial networks has taken these images and just pushed a little bit towards the real frontier and then made it fake. Similarly, this all these domestic animals they took and then they created, you see, they created models of the cats, which is totally not present in the data set, but they are cat. Now, what does it, how does it help? Suppose you only train with this, the accuracy, and if you train with this along with the new generated images, obviously your accuracy will be more because you can now see in many unseen scenarios which may occur, who knows, right? So this is the power of deep learning where it is going, and with all the proliferations of deep learning, I will show you another very interesting image. Have you seen that the photos has been colorized? Is the video visible? I mean, I am not played yet. I just shown a video.
Yes,
Yes,
sir.
sir, it is visible.
Visible.
You can see that there is a grayscale video and totally abrupt a random image of this of a different girl. This is an old picture, old English picture, which is black and white. And what has happened, you see. So what has happened is the fact that you can see that gradually these all images of the old, this is Charlie Chaplin images, this has happened. And there are papers like the 10th position, this paper has a 10th position. So all of this paper, Chromagan has the 9th position. And finally, if you look at the colorings and come up, then finally, if you move with this video, you will see that in the leaderboard right now, there is a something called Deep AI. And finally, Deep AI is also beaten by Deep MyHeritage. So what MyHeritage do, it can take pictures of posthumous people and can make them live. See this one. This is the MyHeritage website. Just adversarial GANs. It's called Stylus GAN, a new research. This lady has died. I mean, you're seeing this. You just upload any of your photo, it animates like this. Look at this one. It has a fixed kind of pose. So even if you change the photo to someone else, the poses will remain the same. All of them is not exist anymore. Okay, so isn't it cool? I mean, isn't it great what deep learning can reach? Okay, so these all are the famous people. I mean, you can just add any of your own known photo and can do this. So this is where we are right now. I mean, what are the frontiers of deep learning that we can reach to? I mean, the next is in your hands. So what you can do? Okay,
That means in future robot may have the human faces.
So no, there is papers like lifelong learning which says that I can tell you, which says that I will place one robot in front of, I mean, in your home, which will just go on with you. Then after you die, that robot will just behave like you. So after you die, I ask something, that robot will answer as you have answered it, because it's a lifelong training has made, and after you die, it just keeps on doing that. So so now you can see why this fairness, biasness, in AI, all this research is now coming up because now the deep fakes and all companies can create anything, right? I mean, it can just forge any person, it can just forge any person's voice and can tell anything, create a social media outrage. So therefore, this bias, fairness in AIs and deep learning are a boom topic that we need to make deep learning and AI to be fair, to do not have to have their integrity itself, do not misuse it. How can you prevent deep learning to misuse something? How can you detect these images are fake? So all these images that I have taken is very recent research work. This is ICLR 2017 work. These images are, I think, ICLR and ICML, the two top conferences in machine learning in 2018 works. And GAN has totally changed the landscape to a large extent. I mean, you can see that all new pictures movies are being colorized. So you can see that the movies are being colorized by using this. What is not there, I can generate a sample. So with that wow factor, I would like to stop today. And if there are any questions, then we can answer. So this is how, in a nutshell, class I can say about deep learning and what the frontiers of deep learning has opened. Yes, Deepak.
Sir,
Suhas.
actually it was me. Sir, when we have we don't have enough training samples, like in the case of in computer security, we don't have a large number of malware data set or kind of thing. So then in that case, there's something called data augmentation. Is it the same thing like we are generating?
No. See, to generate using generative adversarial networks or autoencoders, you need a large sample because the variations otherwise would be abrupt. And therefore, see, as you can see, I will gradually move my fake points towards the real. If I have very few real points, then the gradual movement towards the real boundary is not so well defined, right? Then people can easily catch it's a fake data.
Yes, sir.
Right. For example, there is a statue which you have seen in one pose. Nobody has seen it live. If you perturb it something else, people will easily catch. So therefore, to have this generative adversarial networks, theoretically, there has also been research that how many samples are good for smoother generation and all. What you are talking about is not about this thing. What you are talking about is segmenting the data so that so when you segment the data, what you do, you keep it in a cluster, and the higher density cluster, you make the probability of generating a fake from that cluster, so that your fake becomes real, looks real. It's a totally separate concept. It is not adversarial. It is adversarial, but it is not the generative adversarial or autoencoder directly applied.
Sir. But sir, we can like in the case of GANs, to train it, we need the annotated data, right? First we need it to the discriminator in the training of the discriminator. We will need the real data also, like recognizing whether it is fake or real, right?
Yes,
but after the training, after say we have the limited amount of data and we have trained it well, and after that if we need more data, like we cannot have the annotated data all the time, so we can use it to generate more data, right?
That's the point. Is if you have less data to start with, this generative exploration will not give you the fake or newly generated data as close as it is, because you have many big holes inside it. See, something is not fake. If something is not fake, that means it has been drawn from a population which is dense, but not exactly this thing is present there, right? You agree this? When something is fake but subtle.
Okay.
Now, when you are saying the data is less, that means my fake, if it is not taken from a distribution where it is dense, then I can easily catch that it is fake.
So, but after maybe when firstly we have the enough data, right, to train it, to train it that is going to generate similar to the real data distribution, right? But after this training, we can generate it, right? Without even using the annotated data, we can generate the lot of amount of data for training and for other purpose also. Like we don't have the annotated data all the time.
Yes, yes. So, but no. I mean, I'm saying that you can go on generating annotated data. So, but if you have your starting point is weak, less data, then this is not a very recommended approach. Then your generated data will have a bias. So, why you are generating data? Because you want to train your model. So,
Yes,
if it
sir.
is has a bias, then your model will not perform well in a unknown scenario. Right? That's why if the data that is given to you to learn is less, then this method is not used. You just wait for tomorrow's class where you will use what is something called semi-supervised learning, which will exactly address your question that we have a less data which are labeled. We have a huge distribution, but that are not labeled to us. How can we learn over that?
Okay, sir.
Okay. But generally, we should have a sufficient data to go with this generative network, because the deeper the network is, this autoencoder, GANs and all, as you can see, the network is very deep. More parameters I need to learn and estimate, and therefore more data I need.
Yes, sir.
Yeah.
So, but then if we have enough data to train our generative adversarial network, then we don't even need to create images for training purpose, right? Because we already have that much data
No.
available.
I mean, no. For training purpose, you need separate images. I mean, you need to train this autoencoder. See,
Suppose,
you need data.
yes, sir. So
Yeah,
suppose if I have 1 million training example for
Yes.
my generative adversarial network,
Yes.
and I wish to generate some training examples for some other application.
Okay.
Then instead of using this 1 million training data for my GAN, I can directly use these training data for my other application. I don't even
Yeah,
need
but
to use
no. The
GAN.
reason is that, as I have given the automotive example, you have the training data, but you do not have the corner cases, right? You do not have plane
Yes, sir.
crashing in a bridge. When you are driving in front of you, some plane crashing, you do not have that data.
So then, but in GANs also that we are discarding that data, right? The
No,
corner
but
cases.
with the corner cases we can generate, right? Once you
To
train
gen
the GAN using your traditional 1 million image, I can generate all these corner cases.
So, but for generating corner cases, we need to train our GAN with data corresponding to corner cases.
No. That's what I am saying. What it does is that it starts with a fake thing. It just tries to make the image visibly look not fake. Visibly look not fake means it will not put a ship on the sky. It will put a ship on over the water. That is, visibly it should not be fake, but it could put a ship just on a cup of water. Could also place a ship over a cup of water. Get it?
Okay. Yes, sir, I got it. Yes, sir.
Any other questions? So this is enormous possible. Yeah, Deepak.
Sir, in autoencoder, we are just encoding the like image or something. So, sir, why
No.
there is
What we are doing, not only encoding, we have a decoding part as well. And autoencoder is just taking the salient features and keeping those features for this latent representation.
so, sir, that's what a decoder encoder model do. So, why we call auto encoder?
Oh, because once you train it, it does it automatically. That's why we call it. Once you train it, your decoder and encoder is a fixed thing that you need to hard code it, right, for a particular application. But once you train it, it is automatically applied to anything. That's why it is autoencoder name.
Means, sir, automatic applied to anything means?
I mean, once you train it, this model, if you apply, so suppose I train it with many images, now I apply with a different image set. Once you train this one,
So,
thing,
for
it will
example,
keep
if
on.
we train it with image of dogs, then we
Okay.
don't need to train it again for image of cats, right?
No,
Are you
not
trying to
like
say?
that. Not like that. It's not transfer learning. Don't. I mean, don't mix it with transfer learning. It is not for transfer learning. What I'm saying is that what it will learn, try to understand what it will learn. It will try to learn the weights inside and this here, right?
Yes, sir.
So what does this mean? It means that how to transform the image it will learn. How to transform any image it will learn.
Yes, sir.
Yes,
It
sir.
will not learn to transform only dog or cat image. It will know the transformation procedure. That's what the weight means. If this weight is 0.1, if this weight is 0.3, if this weight is 0.5, while you train, it fixes this weight like this after training. It means you give a new image. I know how I shall proceed to make a latent description of the image. And after you train, that is automatic.
So,
Sir, but sir,
for generalizing this fact, we will need we will need all kinds of data, right? Means
I mean,
for generating the fake
ImageNet,
thing.
you give the ImageNet.
ImageNet, yes, yes.
You give the
Yes,
ImageNet.
yes.
But fake thing is also comes with this perturbation thing and also comes with this discriminative adversarial modeling that you just shift perturb a little bit and see what happens.
Okay.
I mean,
sir,
all this space.
encoder model. Sir, in encoder decoder model of NLP, where we train the model on a language, then it encode and then decode on other model. So
It
why?
does. It does. Yeah.
So what is the difference between this auto and that encoder decoder model?
No. Encoder. See, this auto comes from the machine learning paradigm that it's a model which can be automatically applied. I mean, don't go by why. If you do not like to call it auto, you do not call it. I always do not believe in jargons. So this name who has proposed that paper wrote, it is automatically encoding through this model. That's why he took the auto and he took the encoder. He gave a name like it is auto encoder. So it is nothing that, I mean, see, sometimes you see a paper name which is abbreviated, then say colon, that's the name of the paper. I mean, then you say why you said this. We also give some paper name like secret, and where S stands for something, A stands for something, C stands for something. Why you to call it secret? Secret is some other meaning. It is not like that. He took this thing after training, it can automatically model. So it's an auto encode. It's an encoding process which can be done automatically after training. He named it auto encode, and we follow that name. That's it.
Okay, sir.
I just want to confirm few things. Like in the case of emotion recognition by the speech,
Yeah.
like
Yes.
the RNN will going to give the best results, right? Which model will going to give the best results over there?
Usually RNN, if you go for this emotional or sentiment analysis, usually RNN is used.
Okay.
So, but Urvashi, the point is that sometimes we also use a mixture models, as I have shown in a Gaussian mixture. I mean, there is a long research, standing research has gone over this. So, if you try to write an RNN, it will give you, but in terms of accuracy, maybe someone else will come in and say that I have done something which is more accurate than you are. But your purpose will be solved by RNN. That much I can assure.
That will depend on the application, right? Always that
Absolutely.
will going to depend on the
Absolutely.
application. Like maybe sometimes we'll use the pictorial information, so we'll use the CNN and
Yes.
RNN both things
Yes.
together, like for.
Correct. Absolutely.
Okay, sir. Okay. But basically for this, RNN will perform the best, right?
Yes. Basically, when you have temporal dependencies to determine some outcome, RNN is the best approach.
Okay, sir. Okay, sir. Thank you.
So, is there any
Yeah.
case where RNN is better than LSTM or GRU? Or since they are improved versions, then we should always go for LSTM or GRU?
No, usually, see, when you have long dependencies.
LSTM we will use.
Yeah, Urvashi.
I was just saying LSTM over here we are using to reduce that exploding and that diminishing factor, right?
Also with the intention that which portion is important as a context to carry forward, either the long, short, which memory. right? And that
So we
answers
can.
your question that, see, depending on an application what you want to generate, that depends which we will use. Suppose you are just generating a music one piece after another, then probably just an RNN will help you. Now, if you are determining from a music which portion is which rag it is being played, then you see it is not necessarily the nearby part only matters. Sometimes it's a extension of some of the previous 5 minutes ago a player is playing, that rag is being followed right now. The change in that is dictates certain ragas in music. So therefore you may use LSTM when to forget and when to, right?
Yes, sir.
Yes, sir. Yes,
See,
sir. But
machine
what I'm
learning
trying to ask is,
is yeah, sure.
what I'm trying to ask is that LSTM will always perform better than RNN. Is it true, or there are some cases when
No,
RNN may
there are
perform
cases.
better than LSTM?
No, there are cases. See, LSTM is very much computationally heavy as well. And as you can see, with the new nodes you come in, the new parameters you get into it, if your data set to train is lesser, then your parameter learning will be not that much accurate, right? So in such cases, you may find cases where your LSTM is not a good model, where you do not need such kind of a long short memorization, and also your data set is thin. Why should we learn all the parameters inaccurately rather than learn fewer parameters more accurately? Right?
So means LSTM is inferior when it comes to constraints, right?
It's
Means
absolutely
computation. Yes.
computational as well as the number of parameters
Data
increase.
set. Yes,
You
sir.
know, when you incorporate new nodes like this, the number of parameters also increases. The weights in each of the lines now comes in.
Yes, sir. That's what I'm saying. That then we need more data to train
Yes,
effectively.
yes.
Yes, sir.
Okay, we exceeded our time anyway.